Okay, now we are going to discuss the electrochemistry. So now here it is a combination of electrical energy, that is electricity, and chemistry is a chemical reaction. It's a study of chemical reaction. So electricity is nothing but it's a flow of electron. It's a flow of electron. The electron can migrate. So chemical reaction is nothing but that involves the breakage of bonds. Breakage of bonds and making of bonds with or without the transfer of electron. From one atom to other or from one molecule to other. To other molecule. So electrochemistry actually builds up the relationship between the electricity and the chemical reactions. The electrochemistry actually gives up electrochemistry gives a relationship between electrical energy or electricity and chemical reaction, or in other words we can define this electrochemistry. It is a branch of chemistry. It is a branch of chemistry which deals with the transformation of electrical energy into chemical energy and the chemical energy into electrical energy. So by these definitions, what we are going to say is that there are certain chemical reactions actually generate electricity. There are certain chemical reaction generate electricity. So electricity is nothing but the flow of electron. Now in the chemical reactions, the electron can flow from one atom to another atom. So this electricity is nothing but the flow of electron. Electron can migrate. It's a flow of electron. Now in the chemical reactions, say for example an atom A and B. Now if an atom has a tendency to lose electron, now it gives up electron. The electron can migrate from A to B. Now the flow of electron, the electron is flowing from A to B actually generates an electric current or electricity. Now the flow of electron from A to B, A atom to B. Now this is called as electric currents. The electron can flow from A to B. Here A is, so we need to imagine that the A is likely to lose electron and B is likely to gain electron. Now the chemical reaction that we are concentrating towards to the loss of electron and the gain of electron, which is also called as the loss of electron, is oxidation, and the gain of electron we call it as reductions. So here in the electrochemistry, the chemical reaction that we are concentrating towards oxidations and reductions with or without breaking of bonds or making of bonds. Certain chemical reactions actually involves only the transfer of electrons. Some chemical reactions actually involves the transfer of electrons along with the breaking of bonds and making of bonds. Now in that case, if you take an example, zinc and copper 2 plus. Now when you bring zinc metal in a copper sulfate solutions, a reactions that happens that the zinc will undergo oxidation and copper get reduced. Now zinc get oxidized by removing 2 electron, that is the 2 electron transfer, and the copper will actually accept the 2 electrons, so therefore it actually is zinc 2 plus, so therefore it is 0 oxidation state, it loses electrons, so therefore it is oxidized, and the copper is plus 2 oxidation state goes to 0, so therefore it is reduced. The overall reaction is a redox reactions. So this reactions happens automatically, so without the need of input energy. When you just bring the zinc metal in the presence of copper solutions, the reactions will happen on its own. So this type of reactions we call it as spontaneous reaction. Now here the migration of electron from zinc to copper. So here the 2 electron actually transfer from zinc to copper. Here zinc is likely to donate electron, copper is likely to accept electron. The copper has, the pulling power of copper is more compared to the zinc. The copper has, it actually pull the electron towards itself. Pulling power is more in case of copper. The pulling power of zinc is less. It actually pulls the electron towards itself. So how one can know that the zinc actually donates electron? How one can visualize the things, the flow of electron that actually generates an electric current? So in order to visualize the flow of electron, in order to experience there is a flow of electron, that is the electricity is running. Now we need a cell. That cell we call it as a galvanic cell or voltaic cell. Now if you take a zinc rod, dipped in zinc sulfate solutions contains. Now we need to take another container. So here we have a copper rod dipped in copper sulfate solutions. This is zinc rod, this is copper. Now we need to make an electrical contact between this. Now in order to know there is a flow of electron which is to be connected to an ammeter A. Now zinc loses electron, it actually flows in this direction. So once the electron flow, which is electricity, the ammeter actually deflects. The needle in the ammeter actually shows a deflection that actually indicates that there is a flow of electrons. Zinc rod actually dissolves. So in order to form zinc 2 plus, here the copper, actually copper 2 plus solutions will be there. The 2 electron will be accepted by the copper 2 plus. The copper get reduced. So here the chemical reactions actually generates electricity. The chemical reaction. So this is a chemical reaction that actually generates electricity. That the cell that we are using is called as voltaic cell or galvanic cell. The same way the batteries, fuels, batteries are also works, fuel cells also works. They convert the chemical reactions into electrical energy. Now there are certain chemical reactions. There are certain chemical reaction. There are certain chemical reactions needs electricity in order to occur. Otherwise, these chemical reactions will not happen. Otherwise, say for example, 2H2O will be converted into 2H2 plus oxygen molecule. That the splitting of water molecules, hydrogen gas and oxygen gas. And this type of reactions with the utilization of electrical energy, we call it as electrolysis. So here electrical energy can be used to run chemical reactions. Electrical energy is used to run a chemical reaction. So if you take the detail of these reactions, that is H2O gives rise to H2 plus oxygen. Now here this is 2H2O, so the oxidation state of hydrogen is +1, oxygen is -2, so here it is 0. Now the oxygen loses electron, the electron is transferred from oxygen to hydrogen. The electron is transferred from oxygen to hydrogens. The oxygen get oxidized and this is get reduced. Now naturally the oxygen has more electronegative, so it actually likely to gain the electron. It likely to gain electron, and hydrogen has less electronegative, likely to give electron. So but oxygen is likely to accept electron, that means undergoes reduction. Hydrogen is likely to lose electron, likely that is to give electron, that is oxidations. But in this reactions the reverse is happening. In order to carry out the reactions in such a way that we need an input energy to remove the electron from the oxygen. Oxygen has -2 electron. In order to remove this electron from the oxygen, we need energy. That energy is electrical energy, and hydrogen doesn't accept the electron so easily. So in order to push the electron towards H plus, in order to pull the electron from the oxygen, and in order to push the electron towards hydrogen, we need electrical energy. So in order to carry out this type of reactions, we need a cell. That cell we call it as electrochemical cell. Electrochemical cell, we have a water, we have electrode, so which is connected to a battery. It is connected to a battery, that is a source of electricity. Now it is the water, is filled with water, or one of the, this is we call it as electrode. This we call it as electrode, and this is one electrode, this is another electrode. So one of the electrode, the oxygen bubbles, and another electrode, hydrogen gas is actually bubbles. After passing an electric current through the solutions, through the electrode, the electrolysis can occur. So lysis means the breakage. So you are breaking the water molecule by using electrical energy, that is why called as electrolysis. So usually we have two types of electrodes. One is cathode, another is anode. So at cathode, reductions will be taking place, and anode, oxidations will be taking place. So here the oxidations is actually uh, oxygen is actually undergoes oxidation, so therefore oxygen evolves at anode and hydrogen gas evolves at cathode. Now other applications of electrochemistry by using electrical energy is electrometallurgy. So in electrometallurgy we can extract the metals in its purest form from the solution that contains metals in ionic form. So electrometallurgy actually involves the reduction of metal ions. Now in order to take electrical energy, or in order to pass electricity to a solution, or in order to generate from a chemical reaction, we need a medium. So without the medium the electric current cannot pass through it. We need a medium. That medium we call it as conducting medium. The conducting medium contains usually a conductor. So the conductor is usually a metals. The first case is the metals. Another case is actually an electrolytic solution. The metal usually with respect to electrochemistry, the metal that we are using is platinum, silver, mercury, lead, and so on. So there are different metals that we are using. So these metals is in contact with the electrolytic solutions such as copper sulfate, zinc sulfate, lead nitrate, silver chloride, KCl, NaCl, and so on. So these are called as a electrolytic solutions. These are electrolytes. So we can define what is an electrolyte. So electrolyte are the chemical species. They are capable of conducting electricity. They are chemical substance and capable of conducting electricity. Example is copper sulfate, zinc sulfate, lead nitrate, KCl, NaCl, and so on. So here the metals actually conduct electricity through the flow of electrons. Metals actually conduct through the flow of electron. They allow the flow of electron very easily, and the electrolytes actually conducts electricity through the flow of ions, through the flow of ions. So this is metals, we call it as metallic conductor, and this is, we call it as electrolytic conductor. So with respect to this, we need to define certain terms and terminologies in order to understand better. The first is actually electrolytic conductance. So here there are two terms, the conductance of an electrolyte or electrolytic conductance. We can define the first term, the conductance. So conductance is nothing but the ease in which the electric current or electricity can pass through. So a given medium, that we call it as, if it is more easy to pass the electricity or the flow of electron is easy to pass through a given medium, we call it as a conductance. It is easy to pass to the flow of electron. Now another term that we need to define, that is the resistance. So here there is some force, there is something that retards, there is something that retards the flow of electron or ions. So here we said in the case of electrolyte, the flow of it conducts electricity through the flow of ions. And here we are saying that something that retards the flow of electrons or ions, we call it as a resistance. Or we can call it as a force that actually retards the flow of electrons or ions. We call it as a resistance, and this resistance actually depends upon the nature of the material. Resistance depends upon the nature of material or conductor. In other words, that is directly proportional to the length of the conductor and inversely proportional to area of cross section, the length in centimeter, the area of cross section in centimeter square. So we can, or is directly upon length inversely proportional to the area of cross section, the length in centimeter and area is centimeter square. Now we can take this proportionality constant, R is equal to rho L by A. Now where R is the resistance that depends upon the length, where rho is a constant that depends upon the where rho is a proportionality constant. Rho is a proportionality constant. Now suppose if the length is 1 centimeter and the area is 1 centimeter square, then the R is equal to rho. Now the resistance of specific length and specific cross-sectional area. Now this resistance we call it as, so what we can call this resistance is, it is a resistance offered by a material whose length is 1 centimeter and area of cross section is 1 centimeter square. Now that resistance we call it as, it's specific, it has a specific length and area, so therefore this resistance we call it as a specific resistance. So it's indicated by rho. So this is specific resistance. Specific resistance is the resistance offered by a specific length or a unit length and unit area of cross sections. Unit of resistance is actually ohm. We call it as ohm. Now we can define conductance in other words. We can define conductance, that is the reciprocal of resistance is called a conductance. The reciprocal of the resistance is called as a conductance. Now the G is conductance, where G denotes conductance 1 by R. So this is R is ohm. The reciprocal of ohm is mho. The unit of conductance is actually here. The unit of conductance is mho, or the reverse of this symbol, this. And another, the SI unit of conductance is actually Simon. The SI unit of conductance is Simon. SI unit of specific resistance. Now the specific resistance will be rho L by A. So this is what? So this is the specific resistance. Just get the formula, R into A, L. Now specific resistance, if A is equal to 1 centimeter square and length is equal to 1 centimeter. Now the unit of resistance is actually ohm. Centimeter cancel, will get centimeters. So the unit of specific resistance will be ohm centimeter. Now in order to illustrate this specific resistance, let us take two plates, a conducting plate so this is a two conducting plate. Okay, now just connect it to a battery of terminals positive or negative. Now inside this container, the conducting, in between these conducting plates, we have a solutions. So we have an electrolyte. So because a solution of electrolyte is placed in between the two conducting plates. Now the conducting plates are separated by a distance L centimeter, and it has an area of cross section A in centimeter square. Now if the length is 1 centimeter and area is 1 centimeter square, now the resistance offered by this electrolytic solutions, we call it as Now the resistance offered by these electrolytic solutions, we call it as specific resistance. Specific resistance. If A is equal to, it is A by L into R rho. If A is 1 centimeter square, length is 1 centimeter, then the resistance offered by the container or the solutions is called as specific resistance because it's specific to length and area. Now another terminology, that is specific. Now the resistance, so before that, the resistance is also, the specific resistance is also called as resistivity, also called as resistivity. Now the specific conductance, it's also called as conductivity. Now according to the definitions of specific resistance, R A by L, so this is a specific resistance. Now if you take reciprocal of this, 1 by rho, 1 by R, L by A. Now this is specific resistance. Now the reciprocal of this specific resistance is called as a specific conductance. The reciprocal of specific resistance is called as a specific conductance. Now the symbol of specific conductance is actually kappa. So this is, we call it as kappa. That is equal to 1 by R. The reciprocal of the resistance is G, that is conductance, into L by specific conductance. So it is a conductance the same way that we have defined specific resistance. The conductance offered by a conductor or conducting medium, whose length is 1 centimeter and area of cross section is 1 centimeter square. Now this is, we call it as specific conductance. The specific conductance is due to, if you take a distilled water, it has no ions. Now it is an insulator, it doesn't conduct electricity. Now to the distilled water, if you add 1 gram of NaCl, now it actually conducts electricity. Now we call it as a conductor. Now if you take these solutions, that is the distilled water containing 1 gram of NaCl, put it into this container, the same container that we defined for resistance. Now this is conducting plate separated by 1 centimeter and the area of cross section 1 centimeter square area. Now the conducting power of all the ions that present in this area, in this container, that gives me specific conductance. The conducting power of all the ions we can define in other words, the conducting power of all the ions that present in 1 centimeter cube of the solution. So this has essentially become 1 centimeter cube of the solutions. the conducting power of all the ion that present only in 1 centimeter cube of the solutions, we call it as specific conductance. So with not reference to the specific length and area, just conductance. If it is a specific length and area, we call it specific conductance, and resistance also. Irrespective of the length and area, we call it just resistance. With respect to the specific length and area, we call it as a specific resistance. Now with the unit of specific conductance, now this is kappa is equal to G to L by A. The conductance 1 centimeter, this is 1 centimeter square. Now we'll get centimeter inverse. Now this is conductance is mho or ohm inverse centimeter inverse or mho centimeter inverse. In SI unit it is Simon meter inverse. The unit of specific conductance is Simon meter inverse in the SI unit. So this is what is specific conductance. If we take an example, if an 100 ml, not 1 cm cube of the solution contains, similarly 1 cm cube of the same solutions contains 2 gram of NaCl. So the volume is same irrespective of the amount of the electrolyte. Still it is a specific conductance. It's specific to the volume. Specific conductance, that is the conducting power of all the ions that is present in only in 1 cm cube of the solutions, we call it as specific conductance irrespective of the amount of the electrolyte.